In Phoenix, the asphalt is buckling. Roads that have stood for 40 years are rippling under 118 degrees Fahrenheit heat, forcing closures across the city. Power grids in Texas are running at 97% capacity, closer to failure than they've been outside a winter storm. Across the Southwest, water reservoirs are dropping 3 inches per week. Hospitals in 6 states report heat-related admissions up 340% from the same week last year. The models predicted a hot summer, but nothing like this. You'd think the answer is here on Earth. Climate patterns, ocean currents, atmospheric pressure, but the real driver is 93 million miles away. And right now, it's doing something we've never fully witnessed before. The sun is changing, not over millions of years, but right now, in ways that are rewriting our understanding of how our star actually works. To understand what's happening now, we need to go back to the moment the sun was born. Birth of fire. 4.6 billion years ago, a cloud of hydrogen and helium begins to collapse under its own gravity. The center heats up, 10 million degrees, then 15 million. At that threshold, hydrogen atoms start fusing into helium. The first photon of light from that fusion takes 170,000 years to fight its way out through the dense plasma, bouncing trillions of times before it finally breaks free. When it does, the sun ignites, a newborn star burning 600 million tons of hydrogen every second. It's not an explosion. It's a balance, gravity crushing inward, fusion pressure pushing out. For billions of years, that balance holds. The sun becomes the anchor of our solar system, 99.86% of all the mass, the source of nearly every joule of energy on Earth. We orbit it, depend on it, take our measurements from it. But from the very beginning, the sun was never as stable as we believed. The illusion of constancy. For thousands of years, humans watched the sun rise and set with perfect regularity. Ancient astronomers in Babylon, Greece, and China tracked its path across the sky, calculated solstices, predicted eclipses. The sun became the symbol of constancy itself. In 1838, Claude Pouillet measured the sun's energy output, what we now call the solar constant, 361 watts per square metre at Earth's distance. The name stuck because it seemed true. Day after day, year after year, the sun poured out the same steady light. Even as telescopes improved, the story held. Yes, there were sunspots, dark patches that came and went, but they were curiosities. The sun's total output barely changed, less than 0.1% variation. Predictable, eternal, unchanging. Textbooks taught it, engineers designed solar panels around it, climate models assumed it. The sun was the one variable we didn't have to worry about. Then, in 1859, something happened that changed everything. The Carrington event, September 1st, 1859. Richard Carrington, a British astronomer, was sketching sunspots through his telescope when he saw something no human had witnessed before. 2 brilliant white flares erupted from the sun's surface, so bright they pierced through his filters. Within 17 hours, the storm reached Earth. Telegraph wires across Europe and North America burst into flames. Operators received electric shocks. Some systems kept running with their batteries disconnected, powered by the Auroras alone. The sky turned blood red as far south as Cuba and Hawaii. Gold miners in the Rockies woke at 1 a.m. thinking it was dawn. In some places, you could read a newspaper by aurora light at midnight. The storm carried the energy of 10 billion atomic bombs. If it happened today, estimates put the damage at $2 trillion, with blackouts lasting months across entire continents. What terrified scientists wasn't just what happened, it was realizing how little warning we'd had. The hidden cycles. In the decades after Carrington, astronomers began tracking sunspots with obsessive precision. They counted them, mapped them, watched them drift across the sun's face. Slowly, a pattern emerged. Every 11 years, the number of sunspots rose and fell in a predictable rhythm. At solar minimum, the sun's face went nearly blank. At solar maximum, it erupted with hundreds of dark spots, each one a magnetic vortex larger than Earth. Then came a stranger discovery. The sun's magnetic field didn't just fluctuate, it flipped. Every 11 years, north became south and south became north, a planetary scale reversal written in the dance of charged particles. By the mid-20th century, we had a working model. Solar cycles were as dependable as seasons. Scientists could predict peaks and troughs years in advance, plan satellite launches around them, brace power grids before storms arrived. For decades, that map held true. Until recently, when the sun stopped following the rules. Solar maximum. Solar maximum is the sun at its most restless. Magnetic fields tangle and snap. Sunspots cluster in vast archipelagos, some stretching 100,000 kilometres across. Flares erupt without warning, hurling radiation at the speed of light. These aren't small outbursts. A single X-class flare releases the energy of 1 billion hydrogen bombs. Coronal mass ejections follow, shock waves of plasma weighing billions of tons, carving through space at 3 million km/h. We're in solar maximum right now. Cycle 25 began quietly in late 2019, crept upward through 2021 and 2022, and is peaking sometime in 2024 or 2025. Every solar maximum is different, some roar with activity, others barely whisper. In 2019, when Cycle 25 was forecast, the prediction was clear. This would be a weak cycle, gentler than average, one of the calmest in a century. Sunspot numbers would stay low. Major storms would be rare. This solar maximum was supposed to be quiet, unremarkable, one of the weakest on record. The forecast came from NASA and NOAA in December 2019, refined through 2020. Solar cycle 25 would peak around 2025 with just 115 sunspots at maximum. That number mattered because it sat below the threshold where major geomagnetic storms become frequent. The prediction wasn't a guess. It drew on 13 different models, each weighted by past accuracy, fed with magnetogram data from the sun's polar fields during the previous minimum. Those polar fields had been weak, which historically meant a weak cycle ahead. By early 2020, the consensus had hardened. Solar cycle 25 would rank among the weakest in 200 years, possibly weaker than cycle 24, which had already been the weakest since cycle 14 in 1906. The models agreed, the data supported them, there was no debate. Within 18 months, every single prediction had collapsed. The first anomaly, January 2022. The observed sunspot number hit 143, more than double the forecast of 61. February, 151 against a predicted 68. March, 125 against 74. The divergence wasn't a spike or an outlier month. It was sustained, accelerating, and it didn't stop. Scientists recalibrated. In October 2022, NOAA revised the forecast upward, now predicting a peak of 185 sunspots in early 2024. But the sun kept climbing past that too. By mid-2023, monthly averages were routinely exceeding 160, and the curve showed no sign of flattening. The models hadn't just missed the magnitude, they'd missed the shape of the cycle itself. Solar cycle 25 was rising faster than any cycle since reliable records began in 1755, outpacing even cycle 19, which peaked at 285 in 1958 and triggered auroras visible in Mexico. What no one realized yet was that the sunspots were only the beginning. The X-class flares, May 2024. An X8.7 flare erupted from sunspot region 36664, the strongest since September 2017. Radio blackouts swept across the Pacific. High-frequency communications dropped for 2 hours. GPS signals drifted by meters, enough to ground some aviation systems temporarily. 10 days later, another X-class flare, then another. By mid-2024, the Sun had produced more X-class flares in 6 months than in the previous 3 years combined. Each one stronger than the forecast models had predicted for this point in the cycle, arriving in clusters the Sun wasn't supposed to generate yet. The X-class designation marks flares that emit more than 0.001 watts per square metre of X-ray radiation at Earth's orbit. They disrupt the ionosphere, the layer that reflects radio waves. When that layer gets hammered, everything that depends on it stutters. Shortwave, satellite links, radar. The disruptions lasted minutes to hours, but they were accelerating in frequency. Then the Sun did something it hadn't done in over a decade. The storms begin. In March 2024, the first coronal mass ejection arrived without warning. 1 billion tons of plasma, magnetic field lines twisted into knots, slamming into Earth's magnetosphere at 1.6 million kilometres per hour. The sky over Montana lit up green and red. Then another storm came, and another. By early May, 7th major CMEs had struck in 3 weeks. Airlines rerouted polar flights to avoid radiation exposure at 35,000 feet. Power grids in Scandinavia fluctuated as induced currents surged through transformers. Auroras appeared as far south as Arizona and New Mexico, latitudes that hadn't seen them in 165 years. GPS signals drifted by meters, then tens of meters. Satellite operators put spacecraft into safe mode, orienting solar panels edge-on to the particle stream. Each storm was stronger than the last. Each one lasted longer. The magnetosphere compressed, buckling under the pressure, and the question wasn't whether another storm was coming. It was why they kept accelerating. But the storms weren't the real mystery. It was what they revealed about the Sun's interior. The core. 150 million kilometres away at the centre of the Sun, hydrogen nuclei collide under 250 billion atmospheres of pressure. The temperature is 15 million degrees Celsius. Every second, 600 million tonnes of hydrogen fuse into helium, releasing energy as gamma rays. Those photons begin a slow crawl outward. They're absorbed and re-emitted trillions of times, bouncing through plasma so dense that a single photon takes 100,000 years to travel from the core to the surface. The energy that warms your face today was born before humans built cities. The core rotates once every 27 days, slightly faster than the surface. It contains 34% of the Sun's mass, but only 1.5% of its volume. The fusion rate is governed by temperature, pressure, and the quantum tunneling probability of protons overcoming electromagnetic repulsion. For 4.6 billion years, this process has been stable. The Sun brightens by about 10% every billion years as helium accumulates and the core contracts, but the changes are glacial. Or they were. Scientists have been watching that core for decades, listening to its vibrations. Heliosismology. The Sun rings like a bell. Pressure waves generated by convection in the outer layers ripple through the interior at different frequencies, creating acoustic modes. By measuring Doppler shifts in spectral lines at the surface, scientists can map the Sun's internal structure with precision measured in kilometres. This is heliosismology, the same principle seismologists use to map Earth's core applied to a ball of plasma 109 times wider. Millions of resonant modes, each one probing a different depth and latitude. The data revealed the radiative zone's sharp boundary, the tachocline's shear, the core's differential rotation. The Global Oscillation Network Group has been recording these vibrations since 1995. The frequencies are stable, predictable, tied to the Sun's density profile and sound speed at each layer. They shift slightly over the 11-year cycle as magnetic fields suppress convection, but the changes are small and well understood. In early 2023, instruments at 6 observatories detected a frequency anomaly in low-degree P modes. The shift was 0.03 microhertz, tiny but persistent. By late 2023, 14 separate acoustic modes showed the same drift. The core's sound speed was changing. In 2023, those rhythms started to shift in ways no theory could explain. The frequency shift. The frequencies themselves weren't vanishing. They were drifting, bending into ranges that didn't match 30 years of measurement. Mode after mode, the peaks in the data began sliding away from their expected positions. Heliosseismologists ran the numbers again. They calibrated instruments, checked for instrumental drift, compared datasets across observatories on 3 continents. The drift persisted. By March 2024, 22 distinct acoustic modes showed frequency deviations beyond 3 standard deviations from the baseline. Some modes were speeding up, others were slowing down. The pattern suggested a change in density, in temperature, in something fundamental about the layers those waves travelled through. The core wasn't just ringing differently, it was changing shape. The shift was small, almost imperceptible, but it pointed to something massive happening at the boundary between the core and the radiative zone. The radiative zone. The radiative zone stretches from 0.25 to 0.7 solar radii, a shell of plasma so dense that photons can't travel in straight lines. They scatter, ricochet, get absorbed and re-emitted trillions of times before inching outward. A single photon born in the core will take 170,000 years to cross this zone. It's not empty space. It's a sea of hydrogen and helium crushed to 20 grams per cubic centimetre, heated to 7,000 degrees Celsius at the outer edge, 15,000 degrees Celsius near the core. Energy here moves by radiation alone. No convection, no turbulence, just photons crawling through a maze of particles. The zone is stable, stratified, older than human civilization. Changes here unfold on timescales measured in tens of thousands of years. Unless something accelerates that process. The tachocline. At 0.7 solar radii, the radiative zone meets the convective zone. The boundary is only 15,000 kilometres thick. Astronomers call it the tachocline. It's where the Sun's internal rotation changes abruptly. Below the tachocline, the radiative zone rotates as a solid body, 27 days per rotation at all latitudes. Above it, the convective zone rotates differentially, faster at the equator, slower at the poles. The tachocline is where those two regimes shear past each other. That shear twists magnetic field lines, amplifies them, stretches them into ropes of flux that rise toward the surface. Every sunspot, every flare, every coronal mass ejection traces its origin to this thin layer. The tachocline is the Sun's dynamo, the engine of its magnetic field. And in 2024, acoustic waves passing through it began showing distortions no model predicted. Temperature gradients steepening, rotation rates flickering, magnetic field strengths spiking in localized pockets 200,000 kilometres below the surface. This is where scientists now believe the current surge is originating. Magnetic dynamo. The tachocline is a dynamo. Plasma rising from below meets the rotating outer layers, and the shear between them twists magnetic field lines into spirals, loops, coils of invisible tension. Those twisted lines store energy. When they rise through the convective zone and break through the surface, they become sunspots. When they snap, they release flares. Everything we see on the Sun is the visible consequence of this hidden engine, churning 200,000 kilometres down. It's self-sustaining. The magnetic field shapes the flow of plasma. The flow of plasma regenerates the magnetic field. A feedback loop that has run for 4.6 billion years. A system so finely tuned that its 11-year rhythm has never missed a beat. But dynamos can stutter, surge or reverse, and right now, ours is doing all three. The polarity problem. Every 11 years, the sun's magnetic poles flip. North becomes south, south becomes north. It's as predictable as the cycle itself, a reversal that begins at solar maximum and completes over the course of several months. Cycle 25's reversal started in late 2023, right on schedule. The northern polar field weakened, collapsed, and began to rebuild with opposite polarity. The southern field followed. By early 2024, both poles should have completed the flip. They didn't. The reversal stalled halfway. The northern pole flipped cleanly, but the southern pole froze in a state of near zero field strength, neither old polarity nor new. For months, the sun's global magnetic structure hung in limbo, asymmetric and unbalanced. That instability is now cascading outward, and it's changing the sun's surface in real time. The convective zone. Above the tachocline lies the convective zone, a 200,000 kilometre thick layer where energy moves not by radiation, but by motion. Plasma heats, expands, rises, cools, contracts, sinks. Granules the size of Texas boil and churn across the surface, each one lasting 8 to 20 minutes before collapsing and reforming. This is where magnetic field lines, twisted and coiled in the tachocline, begin their journey upward. They're carried by rising plasma, stretched and distorted by the turbulent flow. When they emerge, they form loops, arches, structures that trap plasma and glow in ultraviolet light. The convective zone is chaos, but it's predictable chaos. The cells have characteristic sizes. The velocities follow known patterns. Helioseismology has mapped its flow for decades, a vast churning engine that operates within tight statistical bounds. In the past year, the convection patterns have become faster, hotter, and far more violent. The surface. At the very top, where plasma finally becomes thin enough to radiate light into space, you find the photosphere. It's the sun's visible surface, a layer only 500 kilometres deep, where temperatures drop to 5,500 degrees Celsius. This is what we see when we look up, the yellow disk that crosses our sky, but it's not solid. It's a roiling ocean of gas, bright and turbulent. Darker patches appear and fade, magnetic knots that suppress the convection beneath them. We call them sunspots. They bloom in pairs, in clusters, in vast archipelagos that can span 100,000 kilometres. When the magnetic field lines snap and reconnect, they release flares, bursts of X-rays and ultraviolet light that cross 150 million kilometres in 8 minutes. The photosphere is only the symptom. Everything you see, every flare, every sunspot, every eruption, is the result of forces that began 200,000 kilometres below. The convection zone lifts the heat. The tachocline twists the field. The dynamo amplifies the energy. And right now, the photosphere is covered in more sunspots than any time since 2001. The sunspot surge. Solar cycle 25 was supposed to be quiet. The forecast from 2019 predicted a peak sunspot number of around 115, weaker than the cycle before it. By early 2024, the actual count was pushing 200. That's not a small error. That's 50 to 100% above prediction, a cycle that's defying every model we had. It's not just the number. The sunspots themselves are larger, more magnetically complex, with field lines that twist and braid in ways that store enormous energy. These are the active regions that produce X-class flares, the ones that can disrupt satellites, knock out power grids, flood Earth's upper atmosphere with radiation. The Sun is supposed to reach its peak in mid-2025, but it's already behaving like a solar maximum in overdrive. Observers are counting spots every day, tracking their growth, their decay, their rotation across the disk. Some regions fade quickly, others persist for weeks, growing denser, more unstable. One active region in particular has been growing for weeks, and it's about to rotate into view of Earth. Active Region 3664. It appeared on the Sun's eastern limb in early May 2024, a sprawling cluster of sunspots that spanned 200,000 kilometres. That's 15 times the diameter of Earth. Astronomers designated it Active Region 3664. Within days, it unleashed a barrage of flares, M-class, then X-class, one after another, each one brighter and more violent than the last. On May 8th, it fired an X1.0 flare. On May 9th, an X2.2. On May 10th, an X3.9, then an X1.1 6 hours later. The magnetic field in that region was so tangled, so overwound, that it couldn't stay stable. Every reconnection event released the energy equivalent of millions of nuclear bombs. This wasn't a single eruption. It was a sustained assault. Active Region 3664 rotated with the Sun, turning slowly toward Earth, and with each rotation, it grew. By May 11th, it was directly facing us, a magnetic monster aimed at our planet. Spacecraft watched the coronal mass ejections lift off the surface, billions of tons of plasma accelerating outward at 1/500 kilometers per second. When it faced Earth, it launched the strongest geomagnetic storm in over 20 years. The May storms. The storm arrived at Earth on May 10, 2024, and within hours the planet's magnetic field was buckling. NOAA issued its first G5 geomagnetic storm warning in 19 years. Power grid operators from Texas to Quebec went on high alert, monitoring transformers for surge currents that could melt copper windings in minutes. Satellites in low Earth orbit tumbled as the atmosphere expanded outward, dragging on their solar panels. GPS signals scattered. Communication networks flickered. And across the continental United States, people looked up to see something most had never witnessed: the Aurora Borealis, shimmering curtains of green and red light reaching as far south as Florida and Arizona. The storm lasted 3 days. When it finally subsided, scientists tallied the data and found something unsettling. The flare from Active Region 3664 was powerful. Yes, but not extraordinary by solar standards. It shouldn't have produced a G5 storm. Other flares of similar strength had barely caused a ripple in Earth's magnetosphere. But the storm raised a question scientists are still grappling with. Why was it so much stronger than the flare's size suggested? The amplification mystery. Over the past 2 years, this pattern has repeated. Solar storms arriving at Earth with more energy than their source flares should carry. In March 2024, a moderate M-class flare triggered auroras visible across Europe. In September 2023, a coronal mass ejection half the expected density still knocked out radio communications across the Atlantic. It's as if the space between the Sun and Earth is no longer neutral. Something is amplifying the storms during their 93 million-mile journey. Some researchers suspect the solar wind itself has changed, grown denser or faster or more turbulent. Others point to anomalies in the interplanetary magnetic field, structures that focus and accelerate the plasma like a lens-bending light. NASA's Parker. Solar probe, flying closer to the Sun than any spacecraft in history, has been measuring these changes directly. Its instruments detect shock waves rippling through the solar wind, regions where the temperature spikes by a factor of 10 in seconds. The data suggests the Sun is not just producing more storms, it's producing storms that interact with their environment differently. To understand that, we need to follow the journey from the Sun's surface to Earth. The corona. Above the photosphere, the visible surface of the Sun, lies the corona. It's the Sun's outer atmosphere, a halo of superheated plasma so tenuous you can see stars through it. During a total solar eclipse, it appears as a pearly white crown stretching millions of kilometers into space. The corona is also inexplicably hot, over 1,000 degrees Celsius, more than 200 times hotter than the surface below it. This is where the solar wind is born. Particles in the corona move so fast they escape the sun's gravity entirely, streaming outward in all directions at speeds exceeding 1,600,000 kilometers per hour. The wind carries the sun's magnetic field with it, dragging field lines out into the solar system like threads pulled from a spinning ball of yarn. When a coronal mass ejection erupts, it tears through this already turbulent environment. The ejected plasma slams into the ambient solar wind, compressing it, heating it further, creating a shock wave that propagates ahead of the main mass. By the time the disturbance reaches Earth's orbit, it's not a single blob of plasma, but a complex layered structure of magnetic fields and particle densities. Lately, the corona has been behaving strangely, hotter, denser, more turbulent than models predict. The coronal heating problem. The surface of the Sun sits at about 500 degrees Celsius. The corona, the wispy outer atmosphere you see during an eclipse, reaches 1,000 degrees Celsius or more. Something is heating the corona from below, but for over a century, no one has been able to prove what. The leading theories involve magnetic field lines snapping and reconnecting, releasing energy in brief bursts. Others point to Alpha-Venn waves rippling through the plasma, their energy dissipating as heat. Still others propose millions of tiny nanoflares, each too small to detect individually, collectively raising the temperature. But observations don't fully match any single model. The corona is too hot, too variable, too turbulent. Instruments aboard the Parker Solar Probe have measured temperatures and magnetic field strengths that defy clean explanations. What if the current surge is the key to solving that century-old puzzle? The solar wind. The sun doesn't just radiate light, it exhales a continuous stream of charged particles, electrons and protons, flowing outward at an average speed of 400 kilometers per second. This is the solar wind and it fills the entire solar system. It shapes the magnetospheres of planets, stripping atmospheres from worlds without strong magnetic fields. Mars lost most of its air this way, Venus too. Earth sits in this river, constantly bombarded, shielded only by its magnetic bubble. During solar maximum, the wind becomes faster, denser, more erratic. Coronal mass ejections embed themselves in the background flow, creating zones of compressed plasma that move like shock waves through space. But the wind speed and density are rising, and that's putting pressure on our shields. Earth's magnetosphere. Earth's magnetosphere is a teardrop-shaped bubble of magnetic field extending roughly 60,000 kilometers toward the Sun and stretching millions of kilometers downwind. It deflects the solar wind, funneling it around the planet like water around a rock. Trapped within this bubble are the Van Allen radiation belts, zones of high-energy particles held in place by the field lines. Satellites navigate carefully to avoid prolonged exposure. Astronauts on the International Space Station orbit below the inner belt, sheltered by Earth's bulk. When a coronal mass ejection arrives, it compresses the day-side magnetosphere, sometimes pushing it inward by half. Magnetic field lines on the night side stretch and snap, releasing energy in bursts that accelerate particles toward the poles. During strong geomagnetic storms, that bubble compresses and sometimes it cracks. The cracks appear at the magnetopores, the boundary where Earth's magnetic field meets the solar wind. When a coronal mass ejection slams into that barrier, the pressure becomes too much. Field lines twist, snap and reconnect in violent bursts called magnetic reconnection events. These aren't gentle openings, they're ruptures, tearing through the magnetic shield in minutes, sometimes seconds. Solar wind pours through the breach, carrying with it charged particles that flood into the magnetosphere. The energy cascades downward, accelerating electrons and protons toward the polar regions at speeds approaching the speed of light. During the May 2024 storms, satellites recorded dozens of reconnection events in a single day. Each one lasted 10 to 20 minutes, but the cumulative effect was enormous. Particles streamed through the cracks, overloading the Van Allen radiation belts and spilling into the upper atmosphere. The more active the sun, the more frequent and severe these breaches become. The auroras. When those particles hit the atmosphere, they collide with oxygen and nitrogen atoms at altitudes between 100 and 400 kilometers. The collisions transfer energy, exciting the atoms into higher energy states. When they drop back down, they release that energy as light. Oxygen at 200 kilometers glows green, the most common aurora color. Higher up, at 300 kilometers and above, oxygen emits deep crimson red. Nitrogen produces violet and blue, streaking across the sky in curtains and arcs that twist and pulse with the rhythm of the solar wind. The colors depend on altitude, atmospheric composition, and the energy of the incoming particles. An aurora isn't just beautiful. It's a visible symptom of invisible violence playing out overhead, a neon sign marking where the magnetosphere is under siege. During strong storms, the auroral oval expands, pushing the lights farther from the poles, painting skies that haven't seen them in generations. This year, auroras have been seen in places they haven't reached in decades. The Southern Lights. In May 2024, the auroras pushed south into Arizona, New Mexico, and Southern California. Reports came in from Madrid, Rome, Beijing. Latitudes at 30 degrees north and south, regions that typically never see the lights, were lit up in shimmering greens and reds. These weren't brief flashes. The displays lasted for hours, visible even through the glow of city lights. Photographers in suburban Dallas captured curtains of green dancing overhead. In Greece, red auroras stretched across the horizon, bright enough to cast shadows. The geomagnetic storm on May 10th drove the auroral oval down to latitudes not reached since the Halloween storms of 2003. For millions, it was their first glimpse of the lights. For scientists, it was confirmation of the cycle's intensity. The auroras are mesmerizing, otherworldly, a cosmic light show that feels like a gift from the universe. But they're also evidence of the energy flooding through the magnetosphere, a reminder that the same forces painting the sky are also threatening the infrastructure below. The auroras are a gift, a spectacle, but they're also a warning of what's flowing through the grid beneath our feet. The grid. The grid beneath your feet is a web of copper and steel, thousands of miles of transmission lines threading through substations, converging at transformers the size of buses. It's designed for predictable loads, for the ebb and flow of human demand, not for the invisible surges that come from space. When a geomagnetic storm strikes, it doesn't just light up the sky. It induces currents in the ground itself, currents that flow into the grid like a slow-building flood. These are geomagnetically induced currents, GICs, and they behave nothing like the electricity the grid was built to handle. They're direct current, low frequency, creeping through lines meant for alternating current. They heat transformers from the inside, saturating their magnetic cores, forcing them to draw reactive power they weren't designed to absorb. Within minutes, temperatures spike, insulation melts, components fail. The grid has no defense against this. Circuit breakers can't trip fast enough. Protective relays don't recognize the threat. A transformer that took 18 months to manufacture can be destroyed in 90 seconds. During the May storms, grid operators detected currents building faster than they'd seen in years. The 1989 blackout. On March 13, 1989, a geomagnetic storm slammed into Earth's magnetosphere with the force of a freight train. In Quebec, the power grid shuddered. Protective systems tripped. Capacitors failed. The Hydro-Quebec network, one of the most stable in North America, collapsed in 90 seconds. 6 million people were plunged into darkness. It was a Monday morning, just before 2:45 a.m. The blackout hit hospitals, traffic lights, water pumps, heating systems in the middle of winter. Train signals went dark. Elevators froze between floors. The Montreal Metro shut down. For 9 hours, the province operated on backup power and hope. Engineers scrambled to restart the grid piece by piece, substation by substation, a process that should have been routine but was now a high-wire act. The storm had melted transformers at the James Bay Transmission Complex, warped components that were never meant to carry that kind of load. The repairs took months. The economic cost ran into the hundreds of millions. And the storm itself, it was classified as a G4, severe but not extreme. That storm was only a G4. The May 2024 event was stronger, and we were lucky it hit at night when demand was low. The transformer problem. Here's the quiet terror that keeps grid engineers awake. High-voltage transformers are not mass-produced. Each one is custom-built, designed for a specific substation, a specific load, a specific voltage. They weigh 300 tons. They take 12 to 18 months to manufacture, and once they're damaged, they can't be repaired. You replace them, or you go dark. The grid has no spare capacity. There are no warehouses full of backup transformers waiting to be deployed. The supply chain is global, fragile, stretched thin. A single transformer failure can force rolling blackouts. A cascading failure, the kind a major geomagnetic storm could trigger during peak demand, could take down entire regions for months. Weeks, if we're lucky. Imagine it hitting on a summer afternoon, air conditioners running, factories humming, demand at its peak. The currents surge, transformers overheat. One fails, then another, then 10. The load shifts to neighbouring substations, overloading them in turn. The cascade spreads across state lines, across borders. The lights go out from Chicago to New York, from Berlin to Warsaw. And the sun isn't done. We're still climbing towards solar maximum. The satellites. Above you, thousands of satellites trace silent arcs through the dark. They orbit at altitudes where Earth's atmosphere thins to almost nothing, where the boundary between air and void begins to blur. Most fly between 300 and 600 kilometers up, circling the planet every 90 minutes. When a solar storm arrives, it doesn't just light up the sky. It heats the upper atmosphere, making it expand outward like a balloon inflating in slow motion. The air becomes thicker at orbital altitude. Drag increases. Satellites slow down. Their orbits decay faster than predicted. Operators burn fuel to climb back to safe altitude, or they watch their spacecraft sink toward re-entry. SpaceX lost 40 Starlink satellites to a single geomagnetic storm in February 2022, each one tumbling back through the atmosphere, burning up over the span of hours. The radiation arrives too, charged particles sleeting through solar panels and electronics, flipping bits in memory, corrupting data. Some satellites go silent, their computers rebooting in the middle of the void. In the past 6 months, satellite operators have reported triple the usual number of anomalies. The GPS drift. GPS satellites orbit higher at 22,500 kilometers, beyond the worst of the atmospheric drag. But they rely on something even more fragile than altitude: timing. Each satellite carries atomic clocks accurate to a few nanoseconds. Your phone triangulates its position by measuring how long signals take to arrive from 4 different satellites. The math requires precision down to billionths of a second, because light travels 30 centimeters every nanosecond. When a solar storm hits, it floods the ionosphere with extra electrons. Radio waves from the satellites bend and slow as they pass through, their paths warped by the charged plasma. The delays are small, measured in microseconds, but enough to throw off the calculations. Your phone shows you on the wrong street. An automated cargo ship drifts off course. High-frequency trading algorithms, synchronized to GPS time, begin making errors worth millions. Precision agriculture equipment, planting seeds in rows 2 centimeters apart, starts to wander. During the May storms, some regions saw positioning errors exceeding 10 metres, enough to make automated systems fail. The radiation threat. The particles arrive hours after the flare. A flood of high-speed protons accelerated to near light speed. They spiral along magnetic field lines, funneling toward the poles, sleeting through anything in their path. At ground level, the atmosphere is thick enough to stop them. But at cruising altitude, 12,000 metres up, the air thins. Passengers on polar routes, flying over Greenland or northern Canada, absorb radiation equivalent to several chest X-rays during a strong storm. Pilots and flight attendants flying those routes hundreds of times a year accumulate doses that approach occupational limits. The FAA monitors space weather forecasts, issuing advisories when particle flux climbs too high. Astronauts on the ISS retreat to the most shielded modules, huddling behind layers of equipment and water tanks. The station orbits at only 400 kilometres, high enough to see the storms, but too low to escape them. A crew caught outside during a major event could receive a lethal dose in minutes. Airlines have been quietly rerouting dozens of flights per week, avoiding polar paths where radiation exposure peaks. The astronauts. Inside the station, there's a module called the sleep station. Its walls are lined with polyethylene, the same plastic in water bottles, layered thick enough to slow some of the incoming particles. When the radiation alarm sounds, astronauts have 15 minutes to get inside and seal the hatch. Outside that room, the aluminum hull stops visible light, but does almost nothing against high-energy protons. A flare in May 2024 delivered radiation levels 50 times higher than normal background. The crew spent 22 hours in the shelter, rationing water, waiting for the all clear. For missions beyond low Earth orbit, there is no shelter thick enough. The Artemis capsule heading to the Moon carries 4 centimetres of shielding. A major solar storm during the 3-day transit could expose the crew to 300 millisieverts, enough to trigger acute radiation sickness. Mars missions face 9 months in open space, where a single storm could end the mission before it begins. The current solar maximum is forcing space agencies to reconsider launch windows and mission timelines. The Prediction Challenge. NOAA's Space Weather Prediction Center runs 6 different models, each trained on decades of solar observations. They watch magnetic field maps from the Solar Dynamics Observatory, tracking sunspot complexity, measuring field gradients that hint at instability. Machine learning algorithms scan for patterns that preceded past flares. The models gave us 48 hours warning before the October storm. They predicted a moderate event, maybe a G3 on the 5-point scale. What arrived was a G4 bordering on G5, with particle flux 10 times higher than forecast. The May event wasn't predicted at all. The active region rotated into view, already erupting. Physicists call it the solar butterfly diagram, a century of data showing where sunspots appear over each 11-year cycle. This cycle, spots are appearing at latitudes that shouldn't be active yet. Flares are clustering in regions the models flagged as stable. The Sun is writing a script no one handed us. The problem is that we're still watching the Sun from the outside. We can't see what's happening inside until it erupts. The Parker Solar Probe. On December 24, 2024, a spacecraft the size of a small car screamed past the Sun at 430,000 miles per hour, close enough to graze the corona. The Parker Solar Probe, 7 years into its mission, completed its 22nd perihelion, skimming just 3.8 million miles above the surface. At that distance, the heat shield glows at 1800 degrees Fahrenheit, while the instruments behind it stay near room temperature. It's the only probe ever built to fly through the birthplace of the solar wind, the place where the Sun's atmosphere tears free and accelerates into space. Ground telescopes see the wind at Earth, 93 million miles downstream, already cooled and stretched. Parker tastes it fresh, measuring magnetic fields and particle velocities seconds after they leave the corona. Each orbit takes it closer. By 2025, it'll pass within 4 million miles, deep enough to sample plasma at 2 million degrees, to feel the shock waves that heat the corona hotter than the surface below. It's sending back data faster than anyone can analyse, terabytes of measurements from a place no human will ever reach. Its latest passes have revealed something unexpected about the magnetic structures near the Sun. The switchbacks. They're called switchbacks. Magnetic field lines that suddenly reverse direction, zigzagging back on themselves like a river that forgot which way it flows. Parker's magnetometers picked them up during the first close pass, structures that shouldn't exist according to every model of how the solar wind behaves. The field is supposed to spiral smoothly outward from the Sun, dragged by rotation into an Archimedean curve. Instead, Parker found kinks, sharp folds where the field flips 180 degrees in seconds. They're scattered through the inner heliosphere like scars in space, each one carrying magnetic energy that never made it into the textbooks. Researchers think switchbacks might solve part of the coronal heating puzzle. Each reversal releases energy as the kink propagates outward, a mechanism that could pump heat into the solar wind long after it leaves the surface. The math suggests a single switchback carries enough energy to accelerate particles to hundreds of kilometres per second. And during the current solar maximum, switchbacks are appearing more frequently and closer to the Sun. The energy budget. The Sun radiates 3.8 × 10⁻26 watts, a number so large it's almost meaningless until you realise Earth intercepts only a half-billionth of it. That tiny fraction, 1,361 watts per square metre at the top of the atmosphere, is called the solar constant. Except it's not constant. Over the 11-year cycle, total solar irradiance varies by about 0.1%, roughly 1.3 watts per square metre. During solar minimum, the Sun dims slightly as magnetic activity drops. During maximum, it brightens as faculae. Those bright regions around sunspots pump out extra light. Satellites have tracked this rhythm for 4 decades, measuring every flicker. But instruments aboard the Total Irradiance Monitor are showing something unexpected. The current maximum is brighter than the cycle predicts, even after accounting for the increased sunspot count. The irradiance curve is running 0.08% higher than the model expected, a small deviation that compounds when you integrate it over months. This suggests the surge isn't just magnetic chaos. The Sun might actually be outputting more energy. The irradiance anomaly. 0.1% doesn't sound like much. It's 1.4 watts per square metre, less than the heat from a nightlight. But Earth's cross-section is 127 million square kilometres. Multiply that nightlight across half a planet, and you're adding 180 terawatts to the system, roughly the output of 180,000 nuclear reactors running at full capacity. Solar physicists at LASP have been cross-referencing the anomaly with old emission source and ACRIM, checking for calibration drift. The signal holds. Spectral measurements show the increase is broadband, not just a spike in ultraviolet or visible light. The Sun is radiating more energy across the entire spectrum, a shift that climate models didn't predict and can't yet explain. Integrated over a year, that 0.1% anomaly delivers an extra 5.6 sigma-21 joules to Earth's atmosphere and oceans. For context, the total energy humans use annually is about 6 kg/20 joules. The excess solar input is nearly 10 times larger than all the coal, oil and gas we burn combined, deposited directly into the climate system with no off switch. Which brings us to the question everyone is asking: is the Sun causing the heat waves? The heat wave connection. Summer 2024 arrives and the thermometers refuse to stop climbing. Phoenix logs 31 consecutive days above 110 degrees Fahrenheit. Death Valley touches 130 degrees Fahrenheit. Europe sees its hottest June on record, with temperatures in Greece and Turkey pushing past 115 degrees Fahrenheit. Heat domes settle over the Midwest, baking crops and buckling highways. Power grids in Texas and California issue conservation warnings as air conditioning demand shatters projections. In India, monsoon rains fail to arrive on schedule, leaving reservoirs at 20-year lows. The timing is impossible to ignore. The solar irradiance spike peaks in late spring. The heat waves crest in midsummer. Social media fills with charts overlaying the two curves, drawing arrows asking the obvious question. Meteorologists field thousands of inquiries. News anchors frame the connection as self-evident. The sun is hotter, therefore Earth is hotter. But the science is clear and more complicated than headlines suggest. The attribution problem. Climate attribution is forensic work. You isolate each forcing factor, quantify its contribution, compare observations against model ensembles run with and without the variable in question. Greenhouse gases, aerosols, volcanic dimming, El Niño sea surface patterns, land use changes, solar cycles. The 2024 heat waves fit the signature of long-term warming with disturbing precision. Nighttime temperatures stay elevated, a hallmark of greenhouse trapping rather than increased daytime insolation. Ocean heat content continues its multi-decade climb, unaffected by short-term solar bumps. Researchers run the numbers. The irradiance increase translates to roughly 0.24 watts per square metre of additional forcing at Earth's surface after accounting for albedo and atmospheric absorption. CO2 and methane increases since pre-industrial times contribute 3.1 watts per square metre. The ratio is stark. The sun's extra 0.1% contributes, but it's a drop compared to the radiative forcing from CO2. The real culprit. May 2024, atmospheric CO2 measurements at Mauna Loa hit 426.9 parts per million, the highest in at least 3 million years. Methane reaches 1,923 parts per billion, driven by wetland emissions and fossil fuel leaks. The greenhouse effect tightens another notch. El Niño persists through early summer, releasing decades of stored ocean heat into the atmosphere. The combination is predictable and predicted. Climate models from the 1990s forecast exactly this trajectory: the accelerating curve, the compounding extremes. Attribution studies will later quantify it with precision. Human-caused climate change made the 2024 heat waves at least 35 times more likely, increasing their peak intensity by 2.1 degrees Celsius. Natural variability, including solar activity, accounts for less than 5% of the observed signal. The sun is a footnote in the heat wave story, a minor character in a tragedy written by fossil carbon. But that doesn't mean the solar surge is harmless. Its threats lie elsewhere. The Internet apocalypse. Imagine a Carrington-class storm arriving not in 1859, but tomorrow morning. The coronal mass ejection crosses 93 million miles in 17 hours, faster than any model predicted. It strikes Earth's magnetosphere at 7:42 a.m. UTC. Within minutes, induced currents surge through power grids on 6 continents. Transformers overheat, winding insulation fails, oil ignites. But the real rupture happens underwater. Undersea fibre optic cables carry 95% of intercontinental data. Every 50 to 100 kilometres, a repeater amplifies the signal, powered by electricity conducted through the cable's copper sheath. Geomagnetically induced currents burn through those repeaters like fuses. Continents go dark digitally. No transatlantic communication, no stock markets, no cloud services spanning oceans. Repair ships must locate and replace hundreds of repeaters per cable, each one 4 miles deep. The work takes months. Scientists estimate a 10% chance of such a storm within the next decade. The economic cost. Lloyd's of London modelled the cost in 2013, then revised it upward twice. A severe geomagnetic storm carries an economic impact between $2 trillion and $10 trillion, comparable to 20 Hurricane Katrinas striking simultaneously. The cascade starts with power. 130 million people lose electricity in the first hour. Within 24 hours, fuel pumps stop, refrigeration fails, water treatment plants go offline, hospitals switch to generators that run for 72 hours if fuel trucks can reach them. They can't. Satellites tumble as their electronics fry. GPS fails. Shipping containers sit at ports with no way to track or route them. Planes are grounded. The just-in-time supply chain, optimized for 3 days of inventory, collapses in 5. Insurance analysts estimate 18 months for full grid restoration in affected regions. Longer if transformer manufacturing can't keep pace with demand. The 1859 storm melted telegraph wires. We've built a civilization on copper and silicon 1,000 times more delicate, and yet most of the world remains unprepared. The mitigation gap. The engineering fixes are known. Utilities can install neutral blocking devices on transformers for $40,000 per unit. Grid operators can train for rapid shutdown protocols that bleed off induced currents before damage occurs. Nations can stockpile spare transformers, which take 18 months to manufacture and weigh 200 tonnes each. NOAA's budget request for 2024 included $1.01 billion for space weather monitoring, a 40% increase. Congress approved $680 million. The European Space Agency's Lagrange mission, designed to give 5 hours of warning instead of 30 minutes, launched 2 years behind schedule with reduced instrument capacity. Some utilities have hardened critical substations, most have not. The cost-benefit calculation is brutal because the event is rare, the expense is immediate, and the executive who spends the money won't be around to claim credit if the disaster never comes. Meanwhile, solar maximum keeps building. The risk climbs while the infrastructure ages and the budget fights continue. Part of the challenge is that solar storms are invisible until they arrive. The warning time. When a coronal mass ejection tears away from the sun, we get maybe 1 to 3 days of warning. The plasma takes time to cross 93 million miles. Flares travel at light speed, so the warning time is 8 minutes, the time it takes their radiation to reach us. That's enough time to put satellites into safe mode, to reroute flights away from polar routes where radiation exposure climbs. Enough time to alert power grid operators, but it's not enough time to move a 400-ton transformer or evacuate a city if the grid goes down in winter. The forecast models track the eruption, estimate its speed and magnetic orientation. A direct hit with southward pointing fields will interact most strongly with Earth's magnetosphere. But the models depend on continuous observations, on satellites watching the sun and the space between. The faster the solar wind, the less warning we get, and recent storms have been moving faster than average. The NOAA satellites. At the L1 Lagrange point, 930,000 miles from Earth, a single satellite keeps watch. NOAA's Deep Space Climate Observatory, DSCOVAR, sits at the gravitational balance between Earth and Sun. It sees the solar wind before it reaches us, measures its speed, density, magnetic field. That data feeds directly into space weather forecasts. DSCOVAR gives us roughly 15 to 60 minutes of advance notice once a storm reaches L1, the final confirmation before impact. It's the sentinel, the last line of warning. DSCOVAR launched in 2015 with a 5-year design life. It's now operating in year 10, running on instruments built for a shorter mission. Components age, sensors drift, redundancy margins shrink. Every month it survives is borrowed time. If DSCOVAR fails before its replacement launches, we lose our primary forecast capability. The backup plan. NASA and NOAA have plans for a replacement, the Space Weather Follow-on mission. It would carry improved instruments, provide better magnetic field measurements, extend the coverage. But funding delays have pushed the launch window into the late 2020s, possibly 2031. The gap is widening. DSCOVR could fail tomorrow or limp along for 2 more years. The replacement might launch in 2029 if budgets hold and schedules don't slip. That leaves a window of vulnerability, years where a satellite failure would blind us to incoming storms. Other satellites provide partial coverage, RCE and WIND, but they're even older, launched in the 1990s. They were never meant to be the primary forecast system. Ground-based observatories watch the sun's surface but can't measure the solar wind directly. The data gap would be real. Meanwhile, the sun continues to surprise us. The June flare. On June 10, 2024, an active region designated AR3697 unleashed an X3.9 flare. The blast ionized the upper atmosphere over the Pacific, severing radio contact with aircraft for 11 minutes. It was one of the strongest eruptions of solar cycle 25 so far. The region had rotated off the visible disk 2 weeks earlier, hidden on the far side. Now it was back, the sun's 27-day rotation bringing it into view again. Observers expected it to have decayed by then. Instead, magnetograms showed the region had reorganized. New flux had emerged from below. The twisted magnetic field lines that store energy for flares had multiplied, and it's grown larger. The persistence mystery. Most active regions on the sun last 5 to 10 days before the magnetic field dissipates. A few survive 2 or 3 rotations, weakening each time. This cycle, several regions have persisted for 4, 5, even 6 passages across the disk. AR3664, the source of the May auroras, lasted through 4 rotations. Each time it reappeared, it produced more flares. The magnetic complexity wasn't fading, it was regenerating, fed by convection currents thousands of kilometres below the surface. Scientists expected these regions to follow the standard decay curve. They didn't. No model predicted this longevity, and no one can explain what's sustaining them. This persistence is one of the clearest signs that something fundamental has changed in the sun's magnetic cycle. The Maunder minimum. Between 1645 and 1715, sunspots nearly disappeared from the solar surface. During those 70 years, astronomers recorded fewer spots than now appear in a single year. The Maunder minimum, as it came to be known, coincided with the coldest decades of the Little Ice Age. Rivers froze solid across Europe. Glaciers advanced through alpine valleys. The sun's 11-year cycle had stalled into a state of near-total magnetic quiescence. When it finally resumed in the 1700s, no one understood why it had stopped or why it restarted. The Maunder minimum is a reminder that the sun's rhythms are not fixed. The dynamo that generates its magnetic field can shift into configurations we've never witnessed in the modern era. Right now, we're experiencing the opposite, a surge that exceeds all forecasts. The pattern break. Every solar cycle has a signature. Cycle 24, which ended in 2019, was quiet. One of the weakest in a century. When scientists first modelled Cycle 25, they expected more of the same, a gentle rise, a modest peak, maybe 115 sunspots at maximum. But by mid-2023, something was wrong. The sunspot count was climbing faster than the models predicted. By early 2024, it had blown past the forecast entirely. Cycle 25 wasn't tracking like Cycle 24 at all. It was tracking like Cycle 19. The most intense solar cycle ever recorded, peaking in 1958 with 285 sunspots. A cycle that delivered auroras as far south as Mexico, knocked out radio stations across North America, and set a benchmark no cycle since has matched. The pattern had broken, and no one could say if it would revert or if this was the new baseline, which means the peak might not be what we expected or when we expected it. The revised forecast. In October 2023, NOAA's Space Weather Prediction Center revised its forecast. The expected sunspot maximum jumped from 115 to 137. Then in April 2024, they revised it again, now 159, possibly higher. But by then, the monthly sunspot count had already hit 171. Some scientists began asking a different question. Had we already passed solar maximum? Or was the true peak still ahead, masked by month-to-month noise? Solar cycles don't have sharp peaks. They plateau. Maximum can last 6 months, sometimes longer, with activity surging and ebbing across that window. You only know you've passed it when the decline becomes unmistakable. So in the spring of 2024, we found ourselves in a strange position. Record sunspot counts, relentless X-class flares, storms every few weeks, but no clear sense of whether we were at the top or still climbing. The uncertainty itself is unsettling. We're navigating a solar maximum we can't predict. The July surge. July 2024 delivered another wave. AR3C738 erupted with an X1.9 flare on July 2nd. AR37Vis63 followed with an X2.3 on July 14th. Each one triggered coronal mass ejections. Each one sparked geomagnetic storms when the plasma clouds arrived 2 or 3 days later. But what stood out wasn't the individual flares. It was the persistence. Most solar cycles see a burst of activity near maximum, then a drop. Cycle 25 wasn't dropping. The sunspot count stayed elevated, the active regions kept forming, the flares kept coming. By mid-July, scientists were talking about a sustained plateau longer than any cycle in decades. The sun was holding at peak intensity, refusing to ease. Power grids braced, satellite operators adjusted orbits, Aurora photographers kept their cameras ready. And then, in mid-July, something shifted, the sudden quiet. On July 23rd, the sunspot count dropped by 40% in 18 hours. The solar wind, which had been screaming past Earth at 620 kilometers per second, slowed to 380. No X-class flares, no coronal mass ejections large enough to warrant alerts. For 72 hours, the sun sat quiet. Satellite operators exhaled. Power grid engineers stood down from emergency protocols. Aurora chasers in Iceland packed up their gear and went home. NOAA's Space Weather Prediction Center issued a statement on July 26th. Peak solar activity may have passed earlier than expected. The data looked like the beginning of a decline, the first real evidence that solar cycle 25 was finally easing toward its eventual minimum. It hadn't. The August eruption. August 4th, 11:17 UTC. Active region 3784 erupted with an X5.8 flare, the strongest of the entire cycle. Within 9 minutes, 3 other regions flared in sequence, each one triggering the next through magnetic connections nobody had mapped. Sympathetic flaring, the textbooks call it. Rare enough that most solar physicists see it once, maybe twice in a career. This wasn't a single eruption. It was 4 overlapping coronal mass ejections, each one carrying 1 billion tons of plasma, all heading toward Earth on converging trajectories. The combined magnetic field strength measured 87 nanoteslas when it hit on August 6th, shattering the record set in 1989. Auroras reached Mexico City, visible through the light pollution at 19 degrees N latitude. The DST index, which tracks geomagnetic storm intensity, bottomed out at -680, a number that appeared on screens and made veteran forecasters go silent. This is the part of the story where scientists realized they were no longer observing a cycle. They were watching an event. The cascade. The first satellites went dark at 0234 UTC on August 7th. 11 high-orbit communication satellites lost attitude control within 20 minutes as onboard electronics fried. By 04 UIS, GPS accuracy had degraded to 40 metres in North America, 120 metres across Europe. At 06 at 12, a transformer station outside Montreal tripped offline. The cascade began. Quebec's grid, still scarred by 1989, had built redundancies, but the induced currents were 3 times stronger than the design threshold. Within 40 minutes, 18 substations across Ontario and New England went into emergency shutdown. By August 9th, the count was 67 satellites total loss, 200 more in safe mode, and rolling blackouts across 14 countries. Air traffic controllers in Scandinavia were routing planes by voice, no data link. The storm's main phase lasted 51 hours, but the aftershocks, smaller eruptions riding the same magnetic channel, kept hitting for 6 more days. But in the silence that followed, scientists noticed something that changed everything they thought they understood. The afterglow. The instruments kept watching. 3 weeks after the storm, the magnetometers at Tromsø still showed field oscillations 12% above baseline. The helioseismic observatories in California and Chile recorded acoustic frequencies that hadn't settled back, as if the sun's interior was still ringing from a bell struck weeks ago. Then the ultraviolet telescopes found it, a diffuse brightening in the 30.4 nanometer line, the wavelength that traces helium emission from the chromosphere. Not a flare, not a transient pulse, but a persistent glow 7% brighter than the solar minimum average, spread across 40 degrees of latitude. It had been there for 19 days, unwavering. Models said the magnetic field should have relaxed by now. The subsurface flows should have resumed their 11-year rhythm. Instead, the sun looked like it had shifted into a state the textbooks didn't describe. Every forecast assumed the cycle would follow the pattern, peak and then decline. This didn't look like a peak, it looked like a threshold. And so we arrive at the question no one wanted to ask. The threshold. What if the sun's magnetic dynamo, the engine 200,000 kilometres deep that drives the 11-year cycle, had crossed into a different regime? Not a flare, not a storm, but a reconfiguration of the flow patterns that generate the field itself. The helioseismic data suggested the tachocline, the shear layer where the dynamo operates, had changed rotation speed by 3%, enough to alter the twist rate of emerging flux tubes. If that shift persists, the next 5 to 15 years could see sustained high activity, storms arriving not in the predictable ramp of a solar maximum, but in irregular bursts from a sun operating outside its historical envelope. Power grids would face repeated stress. Satellite operators would plan for attrition rates 40% higher. GPS accuracy would degrade during periods no forecast anticipated. Climate models would need to separate the sun's new forcing from greenhouse gas trends, a problem that turns attribution studies into arguments. And the auroras, those transient curtains we chase to the Arctic, might become a permanent fixture at latitudes that haven't seen them in 400 years. The uncertainty isn't whether this is happening. It's how long it lasts and whether we're watching a decade-scale anomaly or the beginning of a grand maximum that could span a human lifetime. What comes next depends on what we choose to do with this knowledge. The preparation. By October 2025, grid operators in 14 countries had begun installing 2,800 additional ground-induced current monitors at transformer substations. NASA approved funding for 3 helioseismic imaging satellites, launch window 2027, designed to map subsurface flows with 10 times the spatial resolution of existing instruments. The European Space Agency extended the solar orbiter mission by 6 years. Utilities in Texas, Ontario and Scandinavia started replacing aging transformers with units rated for 200 ampere geomagnetic disturbances, double the previous standard. Satellite manufacturers revise thermal and radiation specs for constellations not yet launched. Air traffic control systems added redundant comm channels that don't rely on high-frequency ionospheric bounce. It's not a crash program, not a headline-grabbing mobilization. It's a quiet recalibration. Infrastructure engineers and space physicists rewriting the assumptions that shaped the systems we built when the sun seemed predictable. Insurance models for satellite loss, contingency protocols for GPS outages, the expected lifespan of a power grid in the 2030s. All of it adjusted for a star that no longer follows the script. But beyond the infrastructure, something more fundamental has shifted. What endures? We thought we knew the rhythm. 11 years, peak to trough, a pattern we could map and model and build around. But the sun, 4.6 billion years into its slow burn, doesn't answer to our timelines. What endures is the relationship itself. 93 million miles of space, a sphere of plasma 109 times wider than Earth, and the quiet fact that everything we are, everything we've built, exists in the narrow band where its light is warm enough to sustain us, but not strong enough to strip our atmosphere away. The flares will keep coming. The models will improve. We'll build better satellites, harden more transformers, carve a little more warning time out of the 8 minutes it takes light to cross the void. But the deeper lesson is older. We orbit a star in constant flux, a furnace that has outlasted every civilization that ever looked up at it. And in the end, what we carry forward is not certainty. It's the awareness that prediction is always provisional, that the star we depend on is still teaching us what it means to live 93 million miles from something vast, indifferent, and utterly necessary. If this journey resonated with you, subscribe for more stories from the edge of the cosmos.